Hello and welcome to today's video for section 5.4. We are going to be talking about a concept known as elementary reactions, which are part of the reaction mechanism, which sheds light and gives us a little bit more information about how chemical reactions work. Because a lot of times when we're looking at a chemical reaction, we're looking at the overall equation that just includes the reactants and the products, and not things that form in between, because most times chemical reactions are actually composed of several steps, whether it's 2, 3, or even more. So we're going to be taking a closer look at elementary reactions, how they work, and how they contribute to an overall chemical reaction. And we're going to use what we learned about the rate laws to help to confirm whether a set of elementary reactions are appropriate for a certain chemical reaction. All right, so the concept of a reaction mechanism, this is just the sum, or really it's the series of all of the elementary steps for a chemical reaction. The chemical reaction itself is the sum of that reaction mechanism when we add up all those steps together. All right, but the reaction mechanism shows us what is reacting with what and in what order. And not only that, but it also sheds light on some things that are formed in the middle of a chemical reaction that we neither started with nor did we end with. So that is pretty useful in determining how exactly a chemical reaction happens. So if we truly want to understand how a chemical reaction works, we need to understand the steps. And in order to understand the steps or to confirm whether a series of steps are appropriate for a chemical reaction, we can use kinetics. So we can use the rate laws that can be determined experimentally to figure out steps that are involved in a chemical reaction. So we're going to use an example here. Reaction between NO2 and CO to get NO and CO2. So this is the overall reaction. And this reaction has a rate law determined through experimentation, just like what we did before. So perhaps they took the starting concentrations of NO2 and CO and manipulated it over a few experiments. And in doing so, they determined that the rate law is equal to K times the concentration of NO2 squared. So that gives us a little bit of information here. All right, well, that means that NO2 is important for figuring out the rate law here for the chemical reaction, and that CO doesn't actually determine how fast our chemical reaction goes. So NO2 to the power of 2 tells us that NO2 is a second order reactant here, and CO is a 0th order reactant here, meaning that if we wrote out this full rate law here, that we would have CO to the power of 0, which is equal to 1, and also why we don't include it here, just to simplify things. All right, so with our overall reaction, we've got 2 proposed steps here, and they all, well, both of them have their own individual rate constants, K1 and K2, K1 for our first step, K2 for our second step. That's always good for you to indicate whenever you are writing out the elementary steps for a reaction. Always make sure that you differentiate between Ks. Because for this reaction and this reaction, the value of K is not going to be the same, right? So K1, K2. So just a few things to note. NO2 plus NO2 yields NO3 and NO. And then in the second step, NO3 plus CO yields NO2 and CO2. So we've got our reactants on the left side here for both reactions. And we've got the products on the right side for both reactions. And we have something that is actually not included in our overall reaction here, and that is NO3. So NO3 is produced in the first step, and then it is used up again in the second step. So that means that we didn't start with it, and we are not ending with it. So it does play a role in our chemical reaction, obviously, because it needs to be used here in the second step. However, since we don't start with it, and we don't end with it, it is what is known as an intermediate, and it's something that will not show up in the overall reaction. But if this reaction is occurring and it's not finished, right? It started and it hasn't finished yet, then if we were to sample the reaction, we would find the presence of NO3 in there, and that would be evidence to tell us, hey, we probably have a good reaction mechanism here because we found NO3 that shows us that NO3 is being produced by one of our steps. Okay, so again, these two steps are called elementary reactions. So they're just the steps for our overall reaction. So this one occurs before this one occurs because number one, we have to form the NO3 in the first step to use in the second step. Yeah, that's pretty much it. So first step, second step, and we can use the elementary reactions to determine the rate law, and we will, if we can figure out which of these is the rate determining step. And that's going to be the slowest one. All right, there's always going to be one step that is considerably slower than the other steps, and that is going to be the one that determines how fast our reaction can go and is therefore the rate determining step. The two elementary reactions that we have here, okay, again, the rate determining step, whether it's this one or this one, gives us information about the molecularity. And that's just the number of species that have to collide in order for our reaction to happen. All right, so both these reactions do have molecularity. Obviously, this one and this one, we got two things colliding together. This one and this one, we got two things colliding together. So they both involve two reactants that have to collide. And the rate determining step, again, whether it's this one or this one, is going to be the one that tells us what the molecularity is of our overall reaction. Okay, so the molecularity could be unimolecular, bimolecular, as it is in both of our steps here. The first one, NO2 and NO2, is going to look like this, where the rate would be equal to K times NO2 squared, since we have two NO2s. The second step would look more like this because we have two different species, NO3 and CO. So it would be K times NO3 times CO. Rarely we'll have what is called a termolecular molecularity, where we need three things to collide together. And this is very rare because in order for this to happen, since this is in one step, these three things have to collide at the same exact time in a very specific orientation. And if they don't, then nothing is going to happen. So we're going to look more at that in the next section in the collision model. But just know that these termolecular steps are going to be very rare. And mainly for the fact that these types of collisions just happen very rarely because they have to be, the three things have to collide at the same time in a very specific way. All right, so now it's time for us to take our elementary steps and determine if it matches not just our overall reaction, but also the rate law. So we're going to look for two things. Do these two steps add together to give us this? That's our first step. And does our rate determining step match the experimentally determined rate law, the K times NO2 squared in this case? So let's go through the first step. All right, overall reaction, two steps, let's add them together. So we're going to add all the reactants together, then we're going to add up all the products and get this. So NO2 plus NO2 from the first step plus NO3 plus CO from the second step. So all the reactants on one side, and then all the products on the other side. So NO3 plus NO, first step, plus NO2 plus CO2, second step, okay? So we added them all up together, and I've already crossed them out, but the ones that I crossed out are the things that we have on both sides. So think back to the spectator ions, where if we have them on both sides, we should eliminate them. So we're gonna do the same thing here. So I have NO2 gas here, and then NO2 gas over here. So I'm going to cross those out, and then I have NO3 over here and NO3 over here. I'm going to cross those out too. So it turns out that I have a reactant that I also have as a product, and then here our intermediate we got to cross out too, because it is both a product in the first step, and then it's used up again in the second step as a reactant. So we end up with NO2 plus CO, yielding NO and CO2, which we have here. So our overall reaction, adding these two up, matches the overall reaction that we started with. Okay, so we have now determined that that first requirement works. Okay, so these two adding up together fits. So the next thing that we want to do is we got to make sure that one of these steps matches up with the rate law. And normally you would be given additional information next to each of the elementary steps, and it would just be slow and fast, right? Just an indication that one of the steps is slower than the other ones. Okay, so we don't have that information, but that's okay. And again, if we were to have more than 2 steps here, we would only have one step indicated as slow, and then the others would be fast. Okay, so luckily we only have 2 steps here. And if you remember, the rate law is equal to K times NO2 squared. So that means that for that rate law to work with our elementary steps, one of these steps needs to have reactants that match the rate law. Okay. So NO3 plus CO does not match NO2 squared. NO2 plus NO2 does. Right? So I have one NO2, I have a second NO2, and since our rate law is K times NO2 squared, that square tells us that we have 2 NO2s as reactants in the rate determining step. Okay. So again, the rate determining step is the step that is a lot slower than the other steps. It's by virtue of being so slow, is going to be what determines the overall rate, how fast the reaction can go. And so that tells us that if we have this elementary step and our rate law is K times NO2 squared, then this must be the slow or rate determining step. And if you were given information here where this says slow and this says fast, well, you can use that to determine what the rate law is if you're not given the rate law. So if this is a slow reaction, this would give us the rate law is equal to K times NO2 times NO2, or NO2 squared. All right, so we're going to wrap this lesson up with a little bit more practice for the reaction mechanism. We're going to do one more problem. So I have an overall reaction here and a experimentally determined rate law, K times NO2 times F2, and I have a reaction mechanism. So we need to determine if this reaction mechanism is acceptable or not. So we're going to take a look at those 2 things that we just did for the previous problem. All right, so overall reaction, 2 steps here. Do these 2 steps add up to this to check that box for our first criteria? So add all these up, add all these up. So I have NO2 plus NO2 plus F plus F2 yields NO2F plus NO2F plus F, okay? So I didn't combine these together here, but we can just take a look, right? NO2 and NO2 don't have either of those over here, so that means I have to have 2 NO2s as reactants, which we do. I have F2, okay? I have one F2 on this side. I have no F2s over here, meaning that this also has to be reflected as a reactant, which we do, okay? Now the last thing we have over here as a reactant is F, which we also have over here as a product of the first reaction. So since it's a product of the first reaction and a reactant of the second reaction, well, guess what? They cancel out because F is an intermediate. So I can cross that out and I can cross that out. And then we're left with the product side over here, NO2F plus NO2F. Don't have that over here. Therefore, we have to have two NO2Fs as products, which we do. All right, so 2NO2 plus F2 yields 2NO2F. The F's cancel out, and when we add these two up together, that gives us an overall reaction. So our first step is, or sorry, our first criteria is met. Now, does our rate determining step match the rate law? A rate determining step is not the fast step, so we can just ignore this. A rate determining step is the slow step. So we can write the rate law of our slow step, if you remember, going all the way back to the molecularity, as the reactants, okay? So the rate is going to be equal to K times the concentration of 1 NO2 times the concentration of 1 F2. So neither of these are taken to the power of 2 or 3 or anything like that. So it's just going to be K times NO2 to the power of 1 times F2 to the power of 1. That matches our rate law. So therefore, our rate determining step matches the rate law. Our second criterion, it has been met. All right, well, I hope that this little practice was helpful. You will have more of these in the homework that you've been given, the problem set for Unit 5. So if you have any questions about this section or about the previous section, I encourage you to email me, and I'll help you out as best as I can. Second thing, our midterm is now next Wednesday. So that means that on Monday and Tuesday, we'll have another chance to review. Well, I guess a couple more chances to review. And again, if you have any questions about the midterm, please send me an email as well. And that is all for our section here in 5.4. So I hope that this was helpful, and I hope that you have a nice day.